Hello, in this lecture we'll answer two questions. In the first question we find out the area of this green triangle, triangle ABC. And in the second question we find out the length of this short line 780 AP equals to x. We have to find out the value of x. So we start with the first question. In the drawing we have the big quadrilateral QABCP. In addition, we know that AQ equals to AC. That is to say, triangle QAC is an associated triangle, and QC is the base of the associated triangle, triangle QAC. We also know that this is angle PQC, that is right angle. This is angle QPC, that is equals to 60 degrees in size. This is 970 PC, that is equals to 4 units. This is angle ABC, that is also equals to 60 degrees in size. This is side AB, that is equals to 5 units in its length. Again, our task is to find out the area of this green triangle, triangle ABC. So in the first step, we will do a construction, that is to say from point A, we will go perpendicular on the base QC of the associated triangle, triangle QAC. Okay, again, from vertex A, we go perpendicular to the base QC of the associated triangle, triangle QAC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and the base QC. This point is point M. Triangle QAC is an associated triangle because AQ equals to AC. QC is the base of this associated triangle, triangle AQC. And we go perpendicular AM to the base QC. So here we can implement rule 22. I'll repeat quickly on rule 22. According to rule 22, the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. In the drawing, we have triangle ABC. Triangle ABC is an associated triangle because AB equals to AC. BC is the base of this associated triangle, triangle ABC. From the vertex A, we do perpendicular AM to the base BC of the associated triangle, triangle ABC. Again, from the vertex A, we do perpendicular AM to the base BC of the associated triangle, triangle ABC. According to this rule, rule 22, the perpendicular AM bisect base BC. Again, the perpendicular AM bisect base BC. That is to say, divides it into two halves. The first half is BM and the second half is MC. And of course, the first half must be equal to the second half. So BM equals to MC. According to rule 22, the perpendicular AM bisect base BC. That is to say, BM equals to MC. We can implement rule 22 in our drawing. In our drawing, if we focus on the associated triangle, triangle AQC, the perpendicular AM to the base QC bisect the base QC. The perpendicular AM bisects base QC. That is to say, the perpendicular AM divides the base QC into two halves. The first half is QM and the second half is MC. And of course, the first half QM equals to the second half MC. So if we define the first half QM as A, then the second half MC must be also equal to A because they are equal to each other according to rule 22. In the next step, we will extend the perpendicular AM by straight line until it touches side PC. Again, we will extend the perpendicular AM by side line until it touches line 7 PC. And we will define the touching point of the extended perpendicular EM with side BC. This point is point M. So actually extended the perpendicular EM, that is absolutely a straight line because it is a perpendicular. We extended the straight line AM by straight line. The result is AN. When you extend the straight line by straight line, the result must be a straight line. Therefore, AN is also a straight line. If you focus on the right side of the straight line AN at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AN at point M? We have this angle that is right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the right big triangle PQC, 90 degrees plus 60 degrees is 150 degrees. Therefore, this third missing angle must be equal to 30 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Therefore, this third missing angle must be equal to 30 degrees in its size. Likewise, in the small right triangle NMC, 90 degrees plus 30 degrees is 120 degrees, and therefore this third missing angle must be equal to 60 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Therefore, this third missing angle must be equal to 60 degrees in its size. It is very easy to see that the big right triangle PQC is similar to the small right triangle NMC according to angle similarity rule. I will explain anyway why the big right triangle PQC is similar to the small right triangle NMC. First of all, this is angle C that equals to 30 degrees in size. Angle C is the common angle that belongs to both triangles. Angle C belongs to the small right triangle NMC, and angle C of course belongs to the big right triangle PQC. So we can write down that angle C equals to itself as a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 60 degrees and therefore they are equal to each other. So if you found out that all the figures of the big right triangle PQC are correspondingly equal to all the figures of the small right triangle NMC. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. If you found out that the big right triangle PQC is similar, this is the sign of similar, to the small right triangle NMC according to angle similarity rule. And from the fact that the big right triangle PQC is similar to the small right triangle NMC, we will derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle MNC over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle PQC. But again, we derive that side NC of the small right triangle MNC over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle PQC. NC is the missing side, so we leave it as it is. Over PC. PC equals to 4 units in its length according to what is given as the question. and it is equals to MC. MC equals to A units in its length according to our definition. Over QC. QC in total equals to A plus A, that is 2A. So if we found out that NC over 4 equals to A over 2A. We have A in the numerator and A in the denominator, so A will get cancelled. So in this side of the equation we left only with 1/2. That equals to NC over 4. So write it down. 1/2 equals to NC over 4. Here we will multiply this equation by 4, and we get that the missing side NC equals to 4 over 2, that is 2. NC equals to 2 units in its length. This is the missing side NC, that equals to 2 units in its length. In the next step, I'll copy the big triangle A and B in a new page, and we will analyze this big triangle, triangle A and B. So actually, this is the big triangle A and B that the common from the original drawing. This big triangle A and B. AB equals to 5 units in its length according to what is given in the question. 60 degrees plus 60 degrees is 120 degrees, and therefore this first missing angle must be equal to 60 degrees in its size. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. So if you found out that triangle A and B is an equilateral triangle. So write it down. Triangle A and B is an equilateral triangle. Why? Because all of its angles are equal to each other. And we also know that in any equilateral triangle, all the sides are equal to each other. AB equals to 5, therefore AN must be also equal to 5, and NB must be also equal to 5 units in its length. So if you found out that this is side NB, that is equals to 5 units in its length. What is the length of the missing side, side CB? From the drawing it is very easy to see that CB equals to NB minus NC. Again, NB minus NC equals to CB. So I write it down. NB, CB equals to NB minus NC. So CB, the missing side CB equals to NB. NB is 5 minus NC. NC is 2. So total CB equals to 5 minus 2, that is 3. CB equals to 3 units in its length. This is the missing side CB, that is equals to 3 units in its length. In the next step, we do another construction, that is to say from point A, we do perpendicular on CB. Again, from point A, we do perpendicular on CB. So actually this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in CB. This point is point O. We will define the length of 9 cm AO as H. In the next step, I will copy the right green triangle AOB in a new page and we will find out the length of side AO that is equals to H. Actually, this is the right green triangle AOB that are coming from the original drawing. This angle equals to 60 degrees in its size, according to what is given as the question. So in this right triangle AOB, sinus 60 degrees equals to AO over AB. Sinus 60 degrees equals to AO over AB. AO equals to H according to our definition. AB equals to 5 units according to what is given as the question. So in total we actually found out that sinus 60 degrees equals to H over 5. Sinus 60 degrees is equal to square root of 3 over 2. So square root of 3 over 2 equals to H over 5. Here we will multiply this equation by 5 and finally we get that H, this inside H equals to 5 times square root of 3 over 2 units in its length. Our task is to find out the area of this green triangle, triangle ABC. So what is the area of triangle ABC? Actually, we know that the area of any triangle equals to the base of the triangle times the height to the base over 2. We'll choose the base of this triangle, the green triangle, triangle ABC as CB. The height to the base is H because H squared centimeters with the base CB over 2. So I shall found out that the area of this green triangle ABC equals to the base CB times the height H over 2. This equals to the base CB times the height H over 2. We already found out that CB equals to 3 units in its length times H. H equals to 5 times square root of 3 over 2 units in its length. And we have to divide it by 2. So in the numerator of this expression in total we have 3 times 5 that is 15 times square root of 3 over 2 times 2 that is 4. Square root of 3, 15 times square root of 3 over 4 in terms of numbers it is equals to 6.5 square units. So if you found out that the area that we're working for this question, that is the area of this green triangle ABC, it is equals to either 15 times square root of 3 over 4 square units in size. In terms of numbers, the area of this triangle ABC, the green triangle ABC, is equals to 6.5 square units in its size. So we finish with the first question. In the next step, I present to you the second question of this lecture and we'll solve it. In the second question, our task is to find out the length of this short line segment AP that is equals to x. We have to find out the value of x. In the drawing, we have a semicircle. We know that this point O is the center of this semicircle. We know that this is line segment PO that is equals to 10 units in its length. This is line segment QP that is equals to 21 units in its length. This is chord QS that is equals to 16 units in its length. This is angle PQS, that is a right angle. Again, our task is to find out the length of this short line segment AP that is equal to x. We have to find out the value of x. So in the first step, we will complete the semicircle to a circle. So we completed the semicircle to a circle, and we will extend line segment QP by straight line until it touches the circle. And we will define the touching point of the extended line segment QP with this circle. This point is point M. In the next step, we will join points S and M together by straight line. By doing all those constructions, we created the periangle SQM. This is periangle SQM. That is equals to 90 degrees in its size. Periangle SQM subset on chord SM. Again, periangle SQM, that is a right angle, subset on chord SM. So here we can implement rule 5. So I pitch quickly on rule 5. According to rule 5, any periangle that is equals to 90 degrees must subset on the diameter of the circle. In the drawing, we have a circle. This is periangle MAN. That is equal to 90 degrees in size, and therefore, according to this rule 5, periangle MAN must subset on the diameter of this circle. And indeed, periangle MAN subset on MN, that is the diameter of this circle. So according to rule 5, any periangle that is equal to 90 degrees in its size must subtend on the diameter of the circle. So we can actually implement rule 5 in our drawing. Why? Because in our drawing, we have periangle MQS that is equal to 90 degrees in its size, and therefore according to rule 5, periangle MQS must subtend on the diameter of this circle. Periangle MQS subtend on SM, and therefore according to rule 5, SM must be the diameter of this circle. So I write it down according to rule 5. Chord SM must be the diameter of this circle. We will define the radius of this circle as r. Point O is the center of this circle, point S is the point of the circle itself, therefore OS is the radius of this circle, that is equals to r according to our definition. Likewise, OM is also the radius of this circle, that is equals to r. In the next step, we will do a construction, that is to say from the center of this circle, that is to say from point O, we will draw perpendicular on QP. Again, from point O, we will draw perpendicular on QP. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and QP. This point is point N. In the next step, we will focus on the big right triangle, triangle QSM. We define angle QMS, this angle is alpha. So in the right triangle SQM, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, it is the sum of the angles in a triangle. In the next step, we will focus on the right small triangle, triangle NOM. In the right small triangle NOM, we have this is angle alpha, this is actually a common angle that belongs to both triangles. Angle alpha belongs to the big right triangle SQM, and angle alpha belongs, of course, to the small right triangle, triangle NOM. So in the small right triangle NOM, this is angle alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in a triangle. It is very easy to see that the big right triangle SQM is similar to the small right triangle, triangle ONM, according to angle similarity rule. I'll prove anyway, and those two right triangles are similar to each other. First of all, this is angle alpha, that is a common angle that belongs to both triangles, so I can write out that angle alpha equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So if you found out that all the three angles of the big right triangle SQM are correspondingly equal to all the three angles of this small right triangle, triangle ONM, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down, and if you found out that the big right triangle SQM is similar, this is the sign of similar, to the small right triangle, triangle ONM, according to angle similarity rule. And from the fact that the big right triangle SQM is similar to the small right triangle, triangle ONM, we will derive that the following relationship exists between their sides. We will derive that side ON of the small right triangle ONM over side QS of the big right triangle SQM is equal to side OM of the small right triangle ONM over side SM of the big right triangle, triangle QSM. Okay, again we will derive that side ON of the small right triangle ONM over side QS of the big right triangle SQM is equal to side OM of the small right triangle ONM over side SM of the big right triangle SQM. ON is the missing side, so we leave it as it is. Over QS. QS equals to 16 units in its length according to what is given us the question. And it is equals to OM. OM is the radius of this circle that is equals to R. Over SM. SM is the diameter of the circle according to rule 5. So SM equals to R. So in total we should find out that ON over 16 equals to R over 2R. We have R in the numerator and R in the denominator, so R will get cancelled. So in this side of the equation we left only with 1/2, that is equals to ON over 16. So if you find out that 1/2 equals to ON over 16, or ON over 16 equals to 1/2. Here we multiply this equation by 16. And we get that the missing side ON is equal to 16 over 2, that is 8. So we should find out that this is the missing side ON, that is equal to 8 units in its length. In the next step, we'll copy this small green right triangle OP and ONP. In the equation, we will implement the Pythagoras theorem on this small green right triangle ONP. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the formation for Pythagoras theorem. So actually, this is the green small right triangle ONP that I copied from the original domain. This small right triangle ONP according to the Pythagoras theorem, P rho squared, that is the square of the hypotenuse, is equal to Pn squared plus NO squared. PO is 10, therefore PO squared is 10 squared, it is 100, and it is equal to Pn squared. Pn is the missing side, so we leave it as it is. It's Pn squared plus NO squared. NO equals to 8, therefore NO squared is 8 squared, it is 64. So in total we should find out that 100 equals to Pn squared plus 64. Here we will subtract 64 from this equation, and finally we get that Pn squared equals to 100 minus 64 is 36. So Pn squared equals to 36. Here we take a root out of this equation, and finally we get that Pn, the missing side Pn, is equal to the square root of 36, that is 6. So if you found out that the missing side Pn is equal to 6 units in its length. So this is the missing side Pn that is equal to 6 units in its length. What is the length of this missing line segment Qn? From the drawing, it is very easy to see that Qn in total equals to Qp minus Np. Again, Qp minus Np equals to Qn. So I write it down. I found out that Qn equals to Qp minus Np. So Qn in total equals to Qp is 21, according to what is given us the question, minus Np. We just right now found out that Np equals to 6 units in its length. So in total, Qn equals to 21 minus 6, that is 15. Qn equals to 15 units in its length. So actually, this is the missing side Qn that is equals to 15 units in its length. The next step, we join points O and Q together by straight line. Point O is the center of this circle, point Q is the point of the circle itself, therefore OQ is the radius of this circle, that is equals to R according to our definition. In the next step, I'll copy the right triangle O and Q in a new page, and we'll implement the Pythagoras theorem on this right triangle O and Q. Side ON equals to 8 units in its length. QN equals to 15 units in its length. And the hypotenuse QO is the radius of the circle that equals to R. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle Q and O that are coming from the original drawing. This right triangle Q and O, according to the Pythagoras theorem, QO squared, that is the square of the hypotenuse, equals to QN squared plus NO squared. So I write it down. QO squared, that is the square of the hypotenuse, is equal to QN squared plus NO squared. QO is R, therefore QO squared is R squared. And it is equals to Qn squared. Qn is 15, therefore Qn squared is 15 squared, that is 225 plus NO squared. NO is 8, therefore NO squared is 8 squared, that is 64. So in total, we found out that R squared equals to 225 plus 64. 225 plus 64 is 289. So R squared equals to 289. Here we'll take a root out of this equation, and finally we get that R, the radius of the circle, is equals to the square root of 289, that is 17. So if you found out that the radius R of this circle is equal to 17 units. OA is also the radius of this circle. And again, OA is also the radius of the circle that is equal to 17 from one side, but from the other side, OA also equals to AP plus PO. Again, AO equals to AP plus PO. So already known, OA equals to AP plus PO. AP is the line segment that we are looking for in this question. This is equals to X plus PO. PO equals to 10 units in itself, according to what is given as the question. Again, AP equals to X and PO equals to 10. From this long equation, we will derive that 17 equals to X plus 10. 17 equals to X plus 10. Here we will subtract 10 from this equation, and finally we get that X equals to 17 minus 10, that is 7. X equals to 7. So if we found out that AP is equals to X, AP is equals to X is equal to 7 units in its length. So the answer to the question is that the length of this line segment AP is equal to X is equal to 7 units. Okay, so we finish with the second question. In the next step, I'll summarize the lecture. Let's start with the first question, of course. Our task in the first question is to find out the area of this green triangle, triangle ABC. So in the drawing we have quadrilateral QABC, quadrilateral QABCP. In addition, we know that AQ equals to AC. That is to say, triangle QAC is an associated triangle, and the base of this associated triangle, triangle QAC, is BC. In addition, we know that this is angle PQC, that is the right angle. This is angle QPC, that is equals to 60 degrees in size. This is line segment PC, that is equals to 4 units in its length. This is angle ABC, that is also equals to 60 degrees in size, and this is side AB, that is equals to 5 units in its length. Again, our task is to find out the area of this green triangle, triangle ABC. So first of all, we did the construction, that is to say, from the vertex A of the associated triangle, triangle ACQ, we do perpendicular on the base QC. Again, from the vertex A, the associated triangle ACQ, we go perpendicular on the base QC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in QC. This point is point M. So here we can implement rule 22. According to rule 22, the perpendicular to the base of an associated triangle bisect the base. Again, the perpendicular to the base of an associated triangle bisect the base. Triangle AQC is an associated triangle, and QC is the base. From the vertex A, we do perpendicular AM. According to rule 22, the perpendicular AM bisects the base QC. Again, the perpendicular QM bisects the base QC. That is to say, the perpendicular AM divides the base QC into two halves. The first half is QM and the second half is MC. The first half QM, of course, equals to the second half MC. If QM is A, the MC must be also equal to A because they are equal to each other. In the next step, we extended the perpendicular AM by a straight line until it touches line segment PC. And we define the touching point of the extended perpendicular AM with side PC, this point is point N. AM is a perpendicular, it is absolutely a straight line. When you extend the straight line AM by straight line, the result is a straight line. When you extend the straight line by straight line, the result must be a straight line. So AN is also a straight line. So if you focus on the right side of the straight line AN at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AN at point M? We have this angle that is the right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the right big triangle PQC, 90 degrees plus 60 degrees is 150 degrees. Therefore, this third missing angle must be equal to 30 degrees in its size according to the rule that the sum of the angles in a triangle is equal to 180 degrees. Therefore, this third missing angle must be equal to 30 degrees in its size. Likewise, in the small right triangle NMC, 90 degrees plus 30 degrees is 120 degrees, and therefore this third missing angle must be equal to 60 degrees in its size according to the sum rule that the sum of the angles in any triangle is equal to 180 degrees. Therefore, this third missing angle must be equal to 60 degrees in its size. It is very easy to see that the big right triangle PQC is similar to the small right triangle NMC according to angle similarity rule. I will explain anyway why the big triangle PQC is similar to the small right triangle NMC. First of all, this angle is a common angle that belongs to both angles. So you can write down that this angle equals to itself as a common angle that belongs to both angles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 60 degrees and therefore they are equal to each other. So if you found out that all the fingers of the big right triangle PQC are corresponding equal to all the fingers of the small right triangle NMC. And therefore those two right triangles are similar to each other according to angle similarity rule. So again, if you found out that the big right triangle PQC is similar, this is the sign of similar to the small right triangle NMC according to angle similarity rule. And for the fact that the big right triangle PQC is similar to the small right triangle NMC, we derive that the following relationship exists between their sides. We will derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle PQC. Repeat again. From the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side NC of the small right triangle NMC over side PC of the big right triangle PQC is equal to side MC of the small right triangle NMC over side QC of the big right triangle PQC. NC is the missing side, so we leave it as it is over PC. PC is 4 according to what is given as the question. And it is equal to MC. MC equals to A units in itself according to our definition over QC. QC in total is A plus 8, that is 2A. So actually found out that NC over 4 equals to A over 2A. We have A in the numerator and A in the denominator, so A will get cancelled. So in this side of the equation, we left only with 1 half equals to NC over 4. NC over 4 equals to 1 half. Here we multiply this equation by 4 and we found out that NC equals to 4 over 2, that is 2. So NC equals to 2 units in itself. This is the missing side NC is equals to 2 units in its length. In the next step, I copied the big triangle A and B in a new page and we analyze this big triangle A and B. This is the big triangle A and B that the common from the original drawing. Side AB equals to 5 units in its length according to what is given as the question. This triangle A and B, 60 degrees plus 60 degrees is 120 degrees. Therefore, this third missing angle must be equal to 60 degrees in its size according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So if you found out that triangle A and B is an equilateral triangle because of the fact that all of its sides are equal to each other. And we know that in any equilateral triangle, all the sides must be equal to each other. So AB equals to 5, therefore AN must be also equal to 5, and B must be also equal to 5 units in its length. So okay, this is side NB is equals to 5 units in its length. What is the length of the missing side CB? From the drawing, it is very easy to see that CB in total equals to NB motion C. Repeat again, CB equals to NB motion C. So CB equals to NB, that is 5. NB equals to 5 units in its length, minus NC, that is 2. So in total CB equals to 5 minus 2, that is 3. This is the missing side CB, it is equals to 3 units in its length. In the next step, we did the construction, that is to say from point A, we do perpendicular on the base CB. Again, from point A, we do perpendicular on CB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the construction. We define the tangent point of the perpendicular from point A and CB. This point is point O. In the next step, I copied the right green triangle A or B in a new page, and we found out the length of the missing side AO that equals to H. So actually, this is the right green triangle AOB that according to the drawing. This right triangle AOB, sin of 60 degrees equals to AO over AB. Again, sin of 60 degrees equals to AO over AB. AO is H, AB is 5, so in total sin of 60 degrees equals to H over 5. Sin of 60 degrees is square root of 3 over 2, so square root of 3 over 2 equals to H over 5. Here we multiply this equation by 5 and finally found out that H equals to 5 times square root of 3 over 2 units in its length. Our task is to find out the area of this green triangle, triangle ABC. We know that the area of any triangle equals to the base of the triangle times the height of the base over 2. We choose the base of this triangle ABC as CB, and the height is H because it's creates 90 degrees with the base CB. So the area of this triangle ABC must be equal to the base CB times the height H over 2. So the area that we are looking for in this question, that is the area of the green triangle ABC, must be equal to the base CB times the height H over 2. CB is 3, and we found out that H equals to 5 times 4 to 3 over 2. So it is 3 times 5 times 4 to 3 over 2, and we have to divide it by 2 again. So in total, we found out that the area of the green triangle ABC equals to, here in this expression we have in the numerator 3 times 5, that is 15, times 4 to 3, over 2 times 2, that is 4. So in total, we actually found out that the area of this green triangle ABC is equals to either 15 times 4 to 3 over 4 square units in its size, or in terms of numbers, the area of this green triangle ABC is equal to 6.5 square units in its size. So we finish with the first question. In the next step, I present to you how we solve the second question of this lecture. In the second question, our task is to find out the length of this short line segment AP that is equals to x. We have to find out the value of x. So in the drawing we have a semicircle. This is point O, that is the center of this semicircle. This is line segment PO, that is equals to 10 units in its length. This is line segment QP, that is equals to 21 units in its length. This is called QS, that is equals to 16 units in its length. This is angle PQS, that is a right angle. Again, our task is to find out the length of this short line segment AP that is equals to x. We have to find out the value of x. So in the first step, we completed the semicircle to a circle, and we extended line segment QP by straight line until it touches the circle. We define the touching point of the extended line segment QP with this circle. This point is point M. In the next step, we join points S and M together by a straight line. By doing all those constructions, we created the peripheral angle SQM. This is peripheral angle SQM, that is a right angle according to what is given in the question. And peripheral angle SQM, that is a right angle, subtend on chord SM. Again, peripheral angle SQM, that is a right angle, subtend on chord SM. And according to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. Again, any peripheral that is equal to 90 degrees in size must subtend on the diameter of the circle. This is peripheral angle SQM, that is the right angle, and therefore peripheral angle SQM according to rule 5 must subtend on the diameter of the circle. Peripheral angle SQM subtend on SM, and therefore according to rule 5, SM must be the diameter of the circle. Again, SM is the diameter of the circle according to rule 5. So point O is the center of the circle, point S is the point of the circle itself, so for OS is the radius of this circle, we define the radius of this circle itself, so OS equals to R. Likewise, OM is also the radius of the circle, that is equals to R according to our definition. In the next step, we did the construction, that is to say from point O, we draw perpendicular on PQ. Again, from point O, that is the center of this circle, we draw perpendicular on PQ. So actually this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. When you find the touching point of the perpendicular from point O and PQ, this point is point M. So in the right triangle QSM, we define this angle as alpha. This angle equals to alpha, this angle equals to 90 degrees, and therefore this third BC angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in a triangle. Likewise, in the small right triangle ONM, this is angle alpha, this angle equals to 90 degrees, and therefore this third BC angle must be equal to 90 degrees minus alpha, because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in a triangle. This is angle alpha, that is a common angle that belongs to both triangles. Angle alpha belongs to the big right triangle SQM, and angle alpha belongs to the small right triangle MON. In the next step, we prove that the big right triangle SQM is similar to the small right triangle ONM. So why those two right triangles are similar to each other? First of all, this is the angle alpha, that is a common angle that belongs to both triangles. So we can write down that the angle alpha equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually prove that all the figures of the right big triangle SQM are correspondingly equal to all the figures of the right small triangle ONM. And therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that the big right triangle SQM is similar to the small right triangle ONM, we will derive that the following relationship exists between their sides. We will derive that side ON of the small right triangle ONM over side QS of the big right triangle SQM is equals to side OM of the small right triangle ONM or side MS of the big right triangle SQM. Repeat again. From the fact that the big right triangle SQM is similar to the small right triangle ONM, we will derive that the following relationship exists between their sides. We will derive that side ON of the small right triangle ONM over side SQ of the big right triangle SQM is equals to side OM of the small right triangle OMN over side SM of the big right triangle SQM. ON is the missing side, so leave it as it is, over SQ. SQ equals to 16 in itself according to what is given as the question. And it is equals to OM. OM is the radius of the circle, that is equals to R. Over MS. MS is the diameter of the circle, that is equals to 2R. So in total, we found out that ON over 16 equals to R over 2R. We have R in the numerator and R in the denominator, so R will get cancelled. So here we left only with 1 half. Equals to ON over 16, or ON over 16 equals to 1 half. Here we multiply this equation by 16 and finally found out that ON equals to 16 over 2, that is 8. So this is the missing side ON, that equals to 8 units in its length. In the next step, we implemented the Pythagoras theorem on this small right triangle ONP. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is the right triangle ONP that I covered from the original domain. This right triangle ONP, according to the Pythagoras theorem, OP squared, that is the square of the hypotenuse, equals to ON squared plus NP squared. Okay, P O squared equals to PN squared plus ON squared. PO is 10, therefore PO squared is 10 squared, that is 100, and it is equals to PN squared. PN is the missing side, so we leave it as it is, plus NO squared. NO is 8, therefore NO squared is 8 squared, that is 64. So in total we found out that 100 equals to PN squared plus 64. Here we subtract 64 from this equation, and we found out that PN squared equals to 100 minus 64, that is 36. So Pn squared equals to 36. Here we took out of this equation and found out that Pn equals to the square root of 36, that is 6. So okay, this is the missing side Pn, that is equals to 6 units in its length. What is the length of the missing line segment Qn? From the drawing it is very easy to see that Qn or Nq in total equals to PQ minus Pn. Again, PQ minus Pn equals to NQ. And again, Qn equals to Qp minus Nq. And again, Qn equals to Qp minus Np. Again, Qn equals to Qp minus Np. So Qn equals to Qp, that is 21 according to what is given in the equation, minus Np, that is 6. So in total Qn equals to 21 minus 6, that is 15. So Qn equals to 15 units in its length. In the next step we join points O and Q together by setting point O is the center of the circle, point Q is the point on the circle itself, therefore OQ is the radius of the circle, that is equal to R according to our definition. In the next step I copy the right triangle QON in a new page, and we implemented the Pythagoras theorem on this right triangle QON. This is the right triangle QON that I copied from the original drawing. This right triangle QON, QO squared, that is the square of the hypotenuse, equals to QN squared plus ON squared. QO is out, therefore QO squared is R squared, and it is equals to QN squared. QN is 15, therefore QN squared is 15 squared, that is 225. Plus ON squared. ON is 8, therefore ON squared is 8 squared, that is 64. So in total we found out that R squared equals to 225 plus 64. 225 plus 64 is 289. So R squared equals to 289. Here we took out of this equation and we found out that the radius R equals to the square root of 289, that is 17. So we found out that the radius R of this circle is equal to 17 units in its length. OA is also the radius of this circle R, that is equal to 17. Again, OA is the radius of the OA is the radius of the circle, that is equal to 17 units in its length. From one side, but from the other side, OA or AO equals to also AP plus PO. Again, AO equals to AP plus PO. So you can write here that OA equals to AP plus PO. AP equals to X, that is the line segment that we are looking for in this question, plus PO, that is 10. AP equals to X, and PO equals to 10. So from this long equation, we derive that 17 equals to X plus 10. Again, 17 equals to X plus 10. Here we subtract the 10 from this equation, and finally found out that X equals to 17 minus 10, that is 7. X equals to 7 units in its length. So that we found out that AP is equals to X is equals to 7 units in its length. Again, the answer to the question is the length of the short line segment AP is equals to X is equal to 7 units. The length of this short line segment AP is equals to X is equal to 7 units. Okay, thank you very much.